Welcome back to this module review of caches. In this lesson I will discuss a second technique in addition to multi-level caches that reduces the miss penalty. This technique gives read misses priority over writes. This brings me to the last fundamental cache question. What happens when we write data? First, let's consider what happens on a write hit. Do we write the new data only to cache or also write to memory? The answer is both have been implemented, both are possible and both have been implemented. In a write through cache, the new data is written both to cache and to memory. The advantage of this approach is that cache and memory are consistent at any time. They contain the same data. A disadvantage is that there are many writes to memory. Every new data word is written to memory. Another technique is a write back cache. That means the new data is only written to cache and only to memory when the block is replaced. The advantage of that is that we have fewer writes to memory because several writes to the same cache block, because usually there are several writes to the same cache block before it is replaced. The disadvantage is, however, that now cache and memory can be inconsistent. They may contain different values, different data for the same word. This brings me to an optimization for a write-through cache. This optimization is called the write buffer. When we read data from memory or from cache, then we want to return the data as soon as possible to the CPU so that the CPU can continue with computing. The writes, on the other hand, are not on the critical path. They can happen in the background. The write buffer stores data until they are written back to memory. Right? The CPU continues and only stalls when the write buffer is full. This is illustrated here in this figure. When we write the cache as well as memory, we write the new data into the cache, if we had a write hit, and into the write buffer, and the write buffer in the background writes the new data back to main memory. This brings me to an optimization for a write back cache. We only need to write back a cache block if it has been written the last time it has been fetched from the main memory. Therefore, we add one bit to every cache block, and that bit indicates if the data has been written, modified, but typically this bit is called the dirty bit. It indicates that data is dirty, that it has been modified. Write back caches typically also have a write buffer, but for replaced dirty blocks. So instead of waiting for the dirty block to be written back to main memory, we get the new block and the CPU can continue while the dirty block is written back to memory in the background. For this reason, the write buffer for write back caches is sometimes also called write back buffer. There's another subtle difference between a write through and a write back cache, and that is that the write through cache can be written while we are doing the tag comparison. Why? Because memory or the write buffer has the most recent up-to-date copy of that block. So if it was a cache miss, it doesn't matter because we still have the cache block, a valid copy of the cache block in memory. For write back caches, we cannot do the same because that may be the only copy, the right copy, that is left in the system. This brings us to one more question regarding caches, and that is what happens on a write miss We write data, but the data is not present in the cache. Again, there are two approaches. The first one is to write allocate or fetch on write. That means we first load the block in cache on a write miss, and then we do exactly the same as for a write hit. The other technique, as the name says, is no write allocate or write count. That means that the block is modified in memory, but it's not loaded into the cache. So in general, the write policy is an element of the Cartesian product of write through and write back times write allocate and no write allocate. Although all combinations are in principle possible, write back caches generally use write allocate, whereas write through caches often use no write allocate. Now I have everything in place to discuss giving the last basic cache optimization techniques, giving read misses priority over writes. As I said before, read misses must be handled as soon as possible because the execution units are hungry, they want to eat, they stall waiting for data. Writes, on the other hand, can happen in the background. But there's a rule that we must maintain, an order we must maintain, and that's the memory order. The memory order tells us that a load should return the value written by the most recent store to that very same address. That means that on a read miss, we must either drain the write buffer or check the write buffer first. Here I have a small demo to illustrate this. We have the variable a in main memory and it contains the value 9. Now the CPU writes a new value 7 to the cache. It doesn't wait until the write is completed, so it writes a becomes 7 into the write buffer. Now the CPU wants to load a. If we now give the load of a, the read of a, priority over write, it would go to the cache or it would go to memory and fetch the wrong value, namely the old value, the value 9. This is not allowed. We must maintain memory order, so the read of a should check the write buffer first and return the value 7. If the data, the newest data, is still in the write buffer. This completes this lesson. Thanks for watching. In the next lesson, I will start a new course on instruction level parallelism, data level parallelism, and thread level parallelism. Hope to see you back.